So this is unsupervised versus supervised learning. I call this talk the lay of the land. You've been hearing, obviously it's pretty early in the morning for me, but you folks have been hearing for the day leading up until now, kind of some use cases and model deployment stories and things like this. This talk is kind of going to step back a little bit and just talk more about machine learning in general. For those of you who have never deployed machine learning or have never actually gotten a model all the way into production yet, you may just be at the beginning stages of what is machine learning. Can I use it to solve the problems that I have? What problems do I have that I can solve with data? And so this talk is meant for kind of those people who are just starting to look at machine learning and want to know more about how we get from, oh, I've got an idea that machine learning might be useful, to an actual concrete idea that has a pathway into production. So it might be a review for some of you, but hopefully I've included enough little interesting tidbits in this talk that it'll be interesting even for machine learning practitioners who are more experienced. So as I said, I want to get a little bit more into the machine learning landscape generally here. So what questions am I trying to answer here? First of all, do I have data on which I can do machine learning? And then second, do I have a problem to which I can apply machine learning and using that data create a solution for that problem? And then an even more kind of subtle and interesting question, should I bother with that? So is machine learning the right solution for this problem? Even though I could use machine learning, should I use machine learning? Is there any advantage to using machine learning? And then finally, what if my problem doesn't match one of the traditional machine learning problems that I hear about that a lot of the services are offering? Can I still use machine learning, or am I kind of lost at that point? And so we'll talk about all these questions. And if a lot of this seems overwhelming, the number of algorithms, the different things you can do with your data, performance metrics, realize that it's not just you. Like, they're still giving away PhDs to people in this subject. There's still enough material there to warrant years and years of study. So there is a lot there, and it can take some time to sift through all that to find the subset of things, which is usually small, that are useful to you in particular. Pardon me. So first, we're going to talk about just at a very high level how you get your data ready for machine learning. So again, this isn't, I'm not going to talk too much about the actual mechanics of getting data into a machine learning system, but I am going to talk about what machine learning ready data kind of looks and feels like, and how you know when you have it. So data takes many shapes and sizes, right? And when we say data, we can mean any number of things. There are databases, which are multiple tables, maybe spread across many machines in many different locations, maybe many different formats, maybe the same data stored in different places in different formats. You also have collections of multimedia files, right? YouTube hosts an enormous amount of data. It's all video, it's all audio streams. There are image collections out there. There are loads and loads of text, just plain unstructured text sitting out on the web. There are log files, right? Log files in the gigabytes and terabytes get accumulated every single day on servers across the country. This is all data. Machine learning in general can't work with just random data, right? You can't just feed ones and zeros into an algorithm. Well, there are some exceptions, but in general, you don't feed ones and zeros into an algorithm and get out useful results. Typically, if you want to get to machine learning as quickly as possible, the quickest way there is to get your data into a tabular format. So what do I mean by tabular format? I mean something like an Excel spreadsheet, right? Something that has rows and columns. One table in the Excel spreadsheet. If you have multiple tables, if you have like a database-like situation where you have multiple tables and relationships between them, you have to do something to get that all down to one row column spreadsheet style data set, one tabular data set. If it isn't in that form, then you've already got a little bit of work to do to get it there. And in some cases, just getting it into that form is the majority of the work. As was mentioned in the last talk, a whole bunch of time is spent just understanding what the data needs to look like and understanding how to get the data that you have into that shape of data that can be used to solve the machine learning problem. So I said briefly a second ago that you need rows and columns in your data, right? You want a tabular data set, a single sheet. So what do I mean in particular by rows and columns? You can't just have any rows and columns. You can't, you know, uh, uh, take all of the bits from a video and put that into a single row and say, there, look, I have a row of data. The rows and columns in general have a shape that's meaningful. So each row in the data usually represents a thing that you want more information about. And that's deliberately vague, but this can be almost anything, right? It depends on your problem. So in churn prediction, if you want to predict whether or not a customer is going to leave a subscription service at the end of the month or at the end of the year, if you're trying to predict which customers will churn from your service, each row in that data set is going to be a customer, because the customer is the thing that you want to know about, right? The customer is the thing on which you're going to make a prediction. Similarly, if you have medical diagnosis, each row is going to be a patient, because the patient is the thing that may or may not have the disease. If each row is a hospital, or each row is some collection of patients, or each row is a doctor, you're kind of out of luck, right? You need to transform your data in some way. If you want to make a prediction about patients, you need a data set that's about patients, where each row is kind of a patient, where it's a patient-based data set. Credit card fraud. So here's like a little bit of a gotcha case, right? In credit card data sets, credit risk data sets, you might have a data set where each row is a person. Of course, this isn't going to work if you're trying to predict whether a transaction is fraudulent or not. If you're trying to predict whether a transaction is fraudulent or not, you need a data set that's based on transactions, right? So each row in the data set should represent a transaction. Again, if you have a customer-based data set, that's kind of the wrong thing. You need to move to a transaction-based data set to make predictions like that in general. And then if you're predicting like the closing price of some stock market, some equities market, some debt market, each row is going to be a day, the day for which you know the closing price in training and you want to know and test. Again, if the data is aggregated so that you have it by hour or by month, that's in general the wrong thing. You want a data set where each row represents a day. That's the easiest way to do machine learning. And then columns. So you have your rows, and now what does each column represent for that row? Each column is a piece of information that you can get about the thing that is represented by the row. So in churn prediction, remember each row was a customer. Each column is going to be some sort of information about that customer. Last month's bill, the number of times support was called, whether or not the customer churned. In training, you're going to need to know that. We'll talk a little bit about that in a second. Medical diagnosis. So you want the output of medical tests on that particular patient, their body temperature, their BMI, whether or not they had some disease. In credit card fraud, maybe you want to know the geolocation of the transaction you're examining, the address of the cardholder, the amount. This is, again, a little bit subtle, right? Each transaction is associated with a user. So just because each row in your data set represents a transaction, it doesn't mean user information can't be in there. You just have to associate that user information, that customer information, with each transaction. So if there's multiple rows that came from the same credit card customer that are transactions on the same credit card, that information will in general be repeated, right? So you'll have the address of the cardholder, that'll be the same for everybody, for every transaction on a particular card. The amount of the transaction will be different in general for every transaction. And then finally, market closing price prediction. Again, you want information about that day for which you're trying to predict the closing price. The opening price that day, maybe the volume on that day, the day of week it is, whether it's Monday or Friday. You also might want information about the previous day as part of this row. There's no reason that you can't incorporate information from the previous day into the current row, into the day that you're looking at. The information from the previous day is still a function of the day you're on, right? You know what the previous day is because you're on a certain day. And so you might want to say, okay, what was the price a day ago? What was the price 5 days ago? This is what the stock market technical analyzers do. They look at the price in previous days, try to use it to predict the price going forward. But each row still represents a day, right? Still represents a point in time. And then the columns in that row can be something like, what was the value at t-5, at t-10, where t is today. Feature engineering. So in general, if you have complex data, so like I said, you might have a whole bunch of text data, you might have a whole bunch of multimedia data, sitting around. Your job as kind of the machine learning practitioner is to reduce these complex data types to features that are usually numeric or categorical in nature. Those are the simplest things for machine learning to deal with. Reducing something to a categorical feature, so a variable that takes a few values like A, B, or C, or high, low, or medium, hot or cold, things like this. A good categorical feature usually doesn't have unique values. So you can't just say, okay, I know the cardholder's name for the credit card, and so I'm just going to use their name as a categorical feature. That's going to be kind of meaningless, right? Because there's so many unique names out there that it's just not going to provide very much information. And moreover, this is a useful feature because people who share the same name in general don't share the same credit card behavior. A good categorical feature is something that doesn't have any unique values and usually is a small set of possible values. So you can't just take any label from your data set, any text string from your data set and say, oh, this is a categorical feature. In general, the more categories you have, the less useful that feature is. So you want to get when you create a categorical feature out of something in your data, you want it to take some kind of small set of possible values. And sometimes this involves aggregating. You might have a label that can take 20 different values, but 10 of those values really mean basically the same thing. And so you aggregate those into some sort of umbrella label to decrease the number of categories for this feature. This is a really common step when you're feature engineering, is to make categorical variables that have sort of an appropriate number of categories. Text data, of course, if you have plain text data, the simplest thing to do is just to count occurrences of words that you think are meaningful in that text data. If you have strings that represent a date or a time, you can extract the bits of that date or time out into different features, the day of the month, the day of the week, etc., hour of the day. Sometimes you have to do this yourself. Sometimes this involves like writing code or fiddling around in a feature editor like BigML's Flatline to get the right sort of features. But in a lot of common cases, platforms like BigML will do this for you. So for the text, for example, we'll decide a list of informative words just based on frequency of occurrence, and then we'll count those. When we go to model that data, we'll use counts of those informative words to create the models. Similarly, for datetime data, we know a bunch of datetime formats, and so if a datetime comes at us, we know how to extract the pieces of that datetime into meaningful features. So some of this is automated, but sometimes you do have to do these things yourself. In particular, if you have a categorical feature, only you kind of know the ontology of these categories, right? Only if you have a variable with 1,000 categories, it's you, the domain expert, who knows something like, oh, but really these 500 categories are basically the same thing. So I'll just reduce those to this one category. I'll give all of those points this one label. And then there's one special case here that I want to mention, that I want to call out kind of specifically, aggregation. So when you have multiple data sets, like let's say you have a database of transactions, and you have the customers associated with those transactions, right? This is a many to one relationship. Each customer might have many transactions associated with them. And so let's say you want to know something, instead of about each transaction, you want to know something about each customer, right? And so there's a really common step you take in data preprocessing for machine learning where you aggregate over the rows of that table. So I want to know something about this customer. I want to do customer segmentation. I want to know whether somebody's a high or low value customer, if you want. And so what you do is you take all the transactions from that customer and you flatten them somehow. You aggregate them into a single row representing the transaction behavior of that customer. You can you can count them. You can say how many transactions are there that this customer did. What's the average amount of the transaction? How many transactions on average do they make per week? What's the standard deviation of the amounts? You can do any sort of aggregation you want, but the point is to take this group of transactions that represent a customer and flatten them down into a single row, into a single set of columns. And so in this way, even if you have a table where you have sort of this many to one relationship, you have many rows in your raw data, and you want to make a prediction about groups of those rows, you can just apply some mathematical function to those groups and get one row per entity that you're looking to make a prediction about. Okay, so now suppose we've done all that. Suppose we've done the kind of the hard work of machine learning, which is understanding the domain, getting the data into this tabular format. Now we're ready to do something. So what exactly do we want to do with this data? And the first thing that's available to us, one of the most obvious things, maybe the first machine learning that was ever done, is the sort of learning that's called supervised learning. And what is supervised learning? So basically, supervised learning is a case where you have this tabular data set, and one of the columns in your data set is special. And we're going to call that either the objective or the target variable or the label. And it's something that we don't know when we're training, or something that we know in the training data, but we don't know at prediction time. And we wish we did know that. So stock market is a good example, right? If you knew what the closing price of the market was going to be, at the beginning of that day, then you could make billions of dollars. And so that represents something that we wish we knew at prediction time. We have all the other information in the data set at prediction time, and we wish we knew this column, but we don't. Again, same for medical diagnosis, right? You have the outputs of all these tests, and you wish you knew whether or not that person had the disease. If you have this training data where you have the right answer, where you have a diagnosis for this person in your training data, then you can use that to do supervised learning to give you a prediction of whether or not the person has the disease based on all of these tests that you've done. So said another way, what supervised learning is going to do is it's going to ingest all of that training data, and it's going to create a program that predicts that value, that objective value, from all the other values in your training data. Or if you want, you say another way, supervised learning uses the training data to create a program that transforms the things you know into the things that you want to know. So it's a really kind of a simple mapping. You say, I have this information, I wish I knew this information. And if you can predict one thing from the other, then you've got a supervised learning problem, you've got kind of a successful modeling situation. So just to drill down a little more on the objective field, probably this is clear already, but just to make it kind of absolutely clear, this is the column in your data set that you don't know in advance, but you wish you did. So churn prediction, you want to know if the customer is going to leave the service. Medical diagnosis, you want to know whether or not the patient has some disease. Credit card fraud, you want to know whether the transaction was fraudulent or not. Market closing price, you want to know the closing price of the market on that day. So again, usually this thing you want to know is either something that happens in the future or something that's a result of human kind of expert annotation of the data. Like in the medical diagnosis case, a human can look at those tests and they can analyze the results of those tests and tell you whether or not the patient has the disease. This is the functionality you're trying to replicate, is that expertise. Similarly with credit card frauds, the transaction is fraudulent, you're not going to find that out until later, but you wish you knew right now so you could do something about it. So that's what the objective field is, something that happens in the future or something that's a result of some analysis. Okay, so that's really it for supervised learning, right? There's not too much more nuance to it than that, and yet we have dozens upon dozens of supervised learning algorithms. And they're all doing basically the same thing. If you look out there are some great papers. One, I believe, is entitled something like, do we need hundreds of supervised learning algorithms to solve supervised learning problems? And the conclusion they come up with in this academic paper is that no, you don't need all of these algorithms. You need some small subset of these algorithms, and you're gonna be able to do all the things in supervised learning that you ever could. So why are there so many of them? Why this proliferation of algorithms, besides the fact that college professors need jobs and so they need to generate these algorithms? Why are there so many of them? And there are a couple of good reasons for the proliferation of algorithms. First of all, different algorithms make different assumptions about the function they're trying to fit. So you learn a decision tree. The underlying assumption when you say I want to use the decision tree is that the function you're trying to learn, the prediction function, the thing that maps the things you know into the things you want, you're imagining that you can construct that with a series of axis aligned splits on the data, with a series of thresholds, right? Like a flow chart. You've seen decision trees before. This is the assumption that you're making, is that something that has that shape can represent the function that I want to learn. On the other end of the spectrum, you have linear models, where you're imagining that the function that you're trying to learn is representable by a linear combination of variables, right? And so that's a very different assumption, that you have that the underlying mathematics of the algorithm is saying very different things about the sort of function that it's going to try to learn. So that can be not a problem, but that can be a source of variance in between from algorithm to algorithm, these underlying assumptions. And then also different algorithms have different performance characteristics, right? So linear models fit very quickly, and you only need a little bit of data to fit them in general. In particular, you only need 2 points to fit a line in a lot of cases. So that's really nice, right? Even though linear models kind of lack the ability to generalize to very complex functions, they have this nice performance characteristic where you can fit them absolutely correctly with only a very little bit of data. On the other hand, other algorithms, you look at deep learning, you look at boosted ensembles of trees, you can fit very, very complex functions with these, but you have tons and tons of data. The right thing depends on the problem you're trying to solve. If the problem you're trying to solve happens to be representable as a linear function of the data, of the input data, then you're fine using linear models. You don't need anything more powerful, and you can sort of reap the benefits of the easiness of the problem by using one of these very simple algorithms. You can fit fast. You don't have to worry about overfitting as much as you do with the more complex algorithms. They're extremely fast for prediction. There's all these benefits to using these simpler algorithms when they happen to be the right thing. So this is a part of the reason why you have so many algorithms. And for those of you who are still confused, here's just a little kind of chart that shows a subset of all of the algorithms that are available in machine learning, kind of a useful subset, and just the ways those things vary on various axes. So amount of data required, linear models require very little, all the way up to deep nets. Deep learning requires a lot. Potential to overfit, linear models, you're probably not going to overfit in a lot of cases. Whereas with deep learning, you're very much in a situation where you're prone to overfitting. Speed, linear models are incredibly fast. Ensembles, deep learning, you're making predictions with hundreds, thousands of trees. You're doing huge amounts of dot products. That's very different, right? That's orders of magnitude slower. And then representational power. Linear models, you've got lines, right? That's what you can use to represent the functions that you're trying to learn. Deep nets, you've got depending on how many hidden layers and hidden units and activation functions you apply in the middle, you can basically represent anything. So this is where you have to start asking yourself kind of questions about how much data do you have, how fast do you need things to go, what does good performance mean to you? Are you willing to sacrifice performance for speed? Trade-offs like this. And we'll talk a little more about that later in the day when I do the model selection talk. Okay, one last way of looking at this here is that there's a triple trade-off in machine learning. So if you have a lot of training data, then you can use that to drive down your prediction error, and you can use algorithms that have more power, algorithms that have more representational power. Similarly, if your training data goes down, your prediction error in general gets higher, and you can't use algorithms that are as powerful. And so there's always this tension between these three things: the power of the algorithm you're using, the quality of the solution you're trying to get, the prediction error, and the training data size that you have. So as you play with one of those parameters, in general, the other two are affected. If you want lower prediction error, it might be nice to use an algorithm with more power, but then you need more training data, right? So it's always a balancing act between these three things. Okay, so that's kind of supervised learning in a nutshell. The very high 10,000 foot view of the things we think about as machine learning practitioners when we're doing supervised learning. So what's unsupervised learning? So let's say I don't have anything to predict, right? I have a data set. I have a nice row column data set. I would like to know something about each row in that data set, but I'm not sure exactly what that is, or what it is not one of the columns in the data. It's something else. So there's a bunch of other things we can do with data that machine learning is very good at. For example, data segmentation. You have a bunch of customers. Again, you want to know what's a nice grouping for these customers. What is this collection of documents about? So let's say each row in your data set is just a string of plain text. What do I have in this data set? What are these documents about? Can you pull out documents that are about a particular thing, some subset of these documents? Some strong correlations in the data set. So maybe I don't have anything in particular I'm interested in predicting, but I'm interested in saying if there's values in this data set, say when this column is really high, is this other column really high? Or when this column is really high, is there an inverse correlation? Is this other column really low? Things like that. Can I find just kind of 1-to-1 or 2-to-1 sort of assertions that are supported by the data? And then also, we're good at kind of finding needles in haystacks, which we'll talk a lot more about tomorrow. Find me some points that are just unusual in this data. Are there things in this data? If I assume the data set is made up of mostly normal points, can you find me the things that are odd in this data set? All of these are instances of unsupervised learning. And what we're trying to do in unsupervised learning is we're trying to create a structure that explains all or part of the data. So just as a couple examples, in the customer segmentation example at the beginning, the thing you're trying to create is groups of data points that are kind of coherent, right? Geometrically coherent, where the data points in each group are close together in some sense. So this is the structure you're imposing on the data, is you're saying you belong in this group, you belong in this group, you belong in this group. And once you have that structure, a new point comes in, you can say, okay, here's how that point fits into the structure, right? You have a new customer, here's which group they belong to. Similarly with anomaly detection, find me some points that are odd in this data. What you're building up there when you do anomaly detection, when you do isolation forest learning, is you're building up a representation of the normal data points, right? So you're constructing this structure that tells you whether or not a data point belongs in this data set. And then when you apply this structure to a new point, you can say, yes, this looks like it belongs in this data set. It looks like a lot of the other points in this data set. Or no, this point looks very strange. It looks very different from all of the points in this data set. So the structure you build up is the structure that tells you that. It tells you how your data is distributed in the space that you've given the algorithm. So just briefly, with each of those little sub-examples of unsupervised learning, here I've got rows and columns to review supervised learning. So we have a data set, we want to make a prediction with it. One of those columns is the thing we want to know in the future. So we're going to use the columns we know to predict the column we don't know, right? So here's, if this is a customer churn data set, and that last column is customer churn, I want to use the rest of the features to predict that last column. So again, you're imagining this little colored table here is a data set where each row is a customer and each column is a feature. So in unsupervised learning, we're going to apply kind of different colors to that table that tell us exactly what we're trying to do. So for example, in clustering, that's pretty clear, right? You're looking at each row of the data and you're assigning it to a group. So here we've decided that these 6 rows break into 3 groups. Some have more people in them, some have less. But the point is that all of these groups are designed to be as geometrically coherent as possible. So you're saying in clustering, these 3 yellow points are similar to one another in the data space. These 2 blue points are similar to one another. This red point is not similar to either of those, so we're going to put that in its own group. This is what clustering does, is kind of discovers these groups automatically. Association rules. So association rules gets at these correlations. You don't know exactly what you're trying to predict, but you'd like to find the relationships that hold true in this data set in a statistically significant way. So association rules will typically be kind of human readable rules of the if-then sort. So if the last month's bill was greater than 200 and the customer calls support more than twice, then the customer usually churns. Rules like that, rules that have just 1 or 2 clauses at the beginning, and then they have a clause at the end. If this, then that. And again, the goal here is to come up with rules like that automatically that your data set supports that are there more often than you would expect them to occur at random, and to kind of measure the strength of those rules also. So when you create an association rules resource at BigML, this is what you get, is rules of this type. And then finally, topic modeling. So topic modeling takes the text in your data set. Often it's applied to data sets that only have a single feature, where each row in the data set is just a single document, but you could have multiple documents in each row. There's no reason why you can't. But for topic modeling, we're going to look at the text in each row, and we're going to say, okay, this is a document. This is a set of words that occur together. They occur together for a reason, and that reason is because the document is about something, right? So when you write a document, when you write an email to somebody, when you write a blog or an article, you use a subset of words in your language that are associated with some topic. If you're writing about politics, you say prime minister and president and parliament and so on. If you're writing about sports, you say ball and goal and play and team and so on. And so you're more likely to write some words basically when you're writing about one topic than another. And this is what topic modeling tries to find. It tries to see the groups of words in your data set that appear together most often. And so typically the output of this will be a lot like clustering. It will be a list of topics, a list of groups of words that appear together often. And each document in your data set will get a score for each topic, indicating that, oh, this document is about maybe these two topics primarily. And some applications here of topic modeling. Use it for discovery in big data sets. I have friends who are lawyers who use this technique. They get a bunch of documents from the prosecution, for example, and they're defense lawyers, and they say, okay, here we're disclosing all these documents to you, and they just want to know what's there. They have no idea, or maybe they're interested in only documents that pertain to a certain subject, and so they feed all of these into topic modeling, and that lets them winnow down fairly quickly the documents that are just garbage designed to obscure the actual content of the data dump they've just been given. And then finally, anomaly detection. This is the needle in the haystack case. We know that this data set that we're given is comprised of things that usually happen, but there are very few rows in this data case we suspect that don't belong. They're odd in one way or another. And so anomaly detectors give you the power to find those rows in the data set, the ones that are weird. Applications here, fraud detection is a really big one that I think we're definitely going to talk about a bit more tomorrow, and also data cleaning. So this is where I've used it in my career most. Is you have a data set, you have the suspicion that some points in the data set are broken. Maybe there are zeros, there's missing data where there's not supposed to be, or maybe there's values that are out of bounds, like infinity, where you've divided by zero somewhere that you didn't mean to. And so this is a great way to find those points that are broken, that don't match any realistic values in the data, and kind of discard those. So you do machine learning on only the data that's well formed. Okay, so now we know a whole bunch of machine learning. Maybe you've got some ideas. We know a whole bunch of machine learning techniques. Oh, I could do this with my data, or I could do that with my data, so on and so forth. Just wait a second. Back up a little bit. Take a few steps back. It's great that you have a data that you have a problem you think ML can solve. That's awesome. But take a moment to consider whether or not you actually should use machine learning to solve that problem. And so, how do you even begin to think about that? So I'm gonna give you maybe some ideas that might help you sort it out. So first of all, let's think about machine learning in terms of expert systems, right? Because that's what we want essentially to come out of a machine learning algorithm, is a system that has some expertise, that can perform some task for us very well. So traditionally, when we would do this, historically, you wanted to invent a computerized expert system to do something like medical diagnosis. You would need two people to help you do this. First, you need an expert. You need a person with domain knowledge and experience. If you're doing medical diagnosis, you need a doctor. If you're doing churn prediction, you need like a salesperson or a CEO. If you're doing autonomous vehicle navigation, you need a pilot of the sort of vehicle that you want to move around. But you need somebody who knows how to do this thing. You need the person whose behavior you're going to try and emulate, right? And then there's the programmer. So the programmer is going to interact with the expert, they're going to talk to the expert, and they're going to formalize that expert's knowledge in a computer program. Now, these might both be the same person, right? You might have a person who's very good at something, who's also a programmer, and so they can program their own knowledge. But you need both of these things. You need the expertise, and you need the programmer. You need the person whose behavior you're trying to emulate, and then you need somebody who can teach the computer how to emulate it. So machine learning, we're going to replace the expert with data, and we're going to replace the algorithm, or replace the programmer with an algorithm. Why would you want to do this? So first of all, data is easier to get sometimes, and also sometimes more reliable than the human experts. So you might already have data laying around that you can use to train a classifier instead of having to go out and find somebody who has the expertise you're looking for. And also, experts are subject to sort of the usual human biases, confirmation bias. Their expertise gets outdated, so on and so forth. Data also, of course, has biases, a whole different set of biases, but they don't have the same biases that humans do. Typically, the biases in data will be different and also a little bit easier to mitigate. Like, you're not going to offend data by not taking what it says at face value. You're not going to offend data by trying to make it more balanced. Data is more manipulable than the human expert, and also in general, the biases are more transparent. So there are tests you can do on the data that tell you whether or not it has some of these failings that humans might. And then also algorithms versus programmers. Algorithms work faster. So instead of weeks to generate a model from an expert, you get an algorithm that can generate it in seconds or minutes from the data. They can generate more complex programs than a human can. And then also they're more modular than human programmers. So if you find an algorithm that performs better than the algorithm you're currently using, you don't need to worry about laying off one algorithm or paying severance to an algorithm. You just replace one algorithm with another. The interfaces to those machine learning algorithms are usually very similar, and so you can kind of swap one out for another without too many problems. And machine learning is a good idea when you can leverage these things, right? That's how you know machine learning is a good idea, is when you're able to leverage these advantages, the data versus the expert, and the programmer, or the algorithm versus the programmer. So here's just 4 cases where this leverage is kind of obvious, just in case you're looking for some cases where this leverage is obvious. First of all, people can't tell you how they do it. So there are cases where everyone can do something, but it's hard for them to explain exactly how they do that thing. Computer vision is a good example. Everyone can recognize, a letter A on the page or a letter B on the page, but nobody can tell you exactly how they do that thing. Well, there's a little curl here, and no, that's probably not a B because there's this little mark here. It's very subtle, right? It's difficult for somebody to explain to a programmer why exactly a letter is a letter. Speech recognition is another good example of this. Everybody can understand speech in their own language, and yet it's very difficult for them to explain exactly how they know what you just said, even though they know it perfectly. Lots of NLP problems are like this. So document classification, you can read a book and you can tell me what it's about, even if some of the words are not words you would expect to see in this book in general. Oh, this is just a metaphor for this. So they're just making an analogy to this other thing. This book is still about this first thing. There's a lot of subtleties in language that humans just know from vast experience that are difficult for computers to pick up on. And then spatial navigation, is a classic one. You want a robot that moves around naturally. That's very hard to program. It's a lot easier to learn from experience. exactly what proper spatial navigation looks like. And there's bonus points here if many people have to do this thing. So this is the bin that autonomous driving falls into. Almost anybody can learn how to drive. Almost anybody who's able-bodied can learn how to drive. But if a whole bunch of people have to do this thing and you can make a computer that does it for them, then you're sitting on kind of $1 million idea, right? One of our partners, one of our early partners at BigML, made a system that looks at an NDA and decides whether or not you should sign that NDA, basically. And so this is something that lots of people have to do all the time. You probably could if you had the time and inclination to kind of really examine the NDA, but nobody wants to do that. So this guy found a little niche, right? It's something that it was difficult to program explicitly, something that humans had to do all the time. So here's your use case for machine learning, right? You can reduce the intellectual burden of everyone with an expert system like this. Number two, when human experts are expensive. So this is the case where it's tough to get your hands on a proper expert for one reason or another. Medical diagnosis, again, you need a doctor to sit with you and diagnose all of these hundreds of cases just to get a data set that has hundreds of rows, which is still pretty small. Game playing at very high levels, so you want to create a program that's extremely good at Go or chess. You have to get somebody who's extremely good at Go or chess to sit with you and explain everything that they do. Again, very expensive, and also like it's difficult for them to explain how they play the game at that level. Another example that we actually solved in the machine learning community quite a while ago is autonomous helicopter piloting. So it's very difficult, again, to program a helicopter controller to have the right balance, to be able to, turn effectively and bank effectively. Helicopters are kind of fussy machines that way, if you've ever tried to fly a model helicopter. But it turns out if you just give somebody who's good at it the controller and you watch what they're doing and use that to build up a data set, you can learn to fly a helicopter pretty well, or the machine can learn to fly a helicopter pretty well. Number three is where everyone gets their own algorithm. So this is cases where you can do machine learning on everyone's data set. So everyone is generating their own data set, and they can all give you enough data to create their own model specific to that person. Obviously, you can't send a programmer out to every single person and have them sit with somebody and explain to you why they think email is spam, for example. This is where you can deploy machine learning pretty effectively. Is okay, everybody's got a data set that has thousands of pieces of emails that are spam or not spam. Maybe they've labeled a lot of those for us, or phone calls or whatever. They've labeled a lot of those things for us. We can just send out machine learning to learn a model for those people, or we can have a general model and send it out to each person to be kind of tweaked to their particular preferences. Location prediction is another great example of this. If you've got your mobile phone, you go to the same places every day on a schedule. This is a good place for machine learning, because again, not everybody's schedule is different, right? So if you want to predict where somebody is going, you have to look at their particular movements. Nobody else's are really going to be super relevant. And then demand prediction, if you have a bunch of restaurants kind of scattered across the country and they're each generating sales every day, it's not necessarily so that everybody's restaurants are going to have the same upticks or downticks in demand across the country. You want to build a model for each restaurant and predict for each restaurant what the demand is going to be for the next week, for the next month, etc. And then the last case I'm going to mention here is where every little bit counts. So there's cases where the performance of the algorithm is the overarching concern, even when you've got very small increments. So in market trading, you're doing some kind of financial modeling, you need that to be exact as possible, right? Even a tiny fraction of accuracy can mean millions of dollars for you one way or the other. So you need performance. Even if a human system is doing 90% of the job, if you can get up to 92% by using a machine, it's worth it. High volume vision tests where mistakes are costly. What I'm thinking of here in particular is early when the US Postal Service adopted computer vision technology to read the zip codes off of envelopes. They made a statement that each % increase in accuracy was worth $1 billion to them. And this was years ago. And so when you get into one of those situations where, again, you need every little bit of performance, and even a tiny movement in the accuracy of your system makes a big difference. This is where machine learning can help you out. It can help you extract that last little bit of value from the data that you have. And then some product recommendation problems. Recently, I heard that McDonald's was deploying a product recommendation problem at their store, and they were able to increase the value of the people coming into the store by 20%, just by recommending the right things, right? Just by saying, hey, oh, you got X, you probably want X, or you forgot X, which almost everybody gets along with what you've already gotten. And so they were able to kind of serve their customers a little better, make a little more money by recommending the right products. And so that's just free money to them, right? They're just increasing sales with virtually no work other than the work needed to deploy the machine learning model. It's not like they needed to hire a bunch more employees or to open additional stores or to develop new product lines. This is just selling more of what they already have. And so again, these little increments are going to make a difference for them because it's basically kind of pure profit. Not pure profit, of course, because they need raw materials, but just an uptick in sales that comes from better analytics. And then some negative examples. So there's always another side to this coin, right? There's lots of examples in NLP and computer vision where human experts are cheap and easy to come by, right? So if you want somebody to read the paper each day and pick out the stories that are relevant to you, maybe you could design an expert system to do this, but a lot of times you don't need to, right? If you can just read the paper on your own, everybody is fine to sift through the stories that are relevant and find them on their own. You don't need, it doesn't provide any value to build the system, essentially, right? You've got human expertise that's perfectly adequate, and it's not a problem for people to exercise that expertise. So this is a place where machine learning is not particularly valuable. And there's a lot of cases in which the performance of humans is slightly better than machines. Even though it's slower and more expensive to hire somebody, you need that performance. So this is the opposite of where you can use machine learning to kind of extract the last little bit of performance out of a system. This is the opposite of that case, right? Where you have a human, they're doing a little bit better, even though they're slower and more expensive. If every bit of performance counts, then slower and more expensive is going to win. So again, a place where machine learning is going to lose is where their performance is worse, even if it's better on some axes, even if it's cheaper, even if it's cheaper, and even if it's faster. If it's not quite as accurate, then that might not be good enough. And then a sneaky place here is where a competent program can be written by hand. So you might be looking at a machine learning situation where, oh, I would love to use machine learning to solve this problem. I've got a data set that I can use machine learning for, but also if I just program in, a couple dozen rules by hand, I get performance that's mostly as good, and I avoid the complexities of machine learning, right? I avoid all of this data cleaning. I avoid keeping the model up to date. Of course, now I have to keep my handwritten rules up to date, but it's possible that handwritten rules have kind of higher bias, and they'll survive concept drift a little better than a machine learning model would. So again, you don't want to introduce the complexity of machine learning unless there's some kind of win in it for you. If you can easily program a solution without using machine learning, then that on kind of a cost and effort basis is often going to be the easier thing to do. And then finally, if you can't get the data, right, we rely on machine learning having advantages in terms of data and algorithm versus expert and programmer. If the data is difficult to acquire and or to label, then of course you don't have the fuel for the algorithm, and so you're not going to be able to do proper machine learning, or you're only going to be able to do a little bit of it.
Hi, Charlie. Just quick reminder, you have 5 more minutes for the presentation because we would like to have also a couple of minutes to answer some questions.
Yep, I should be done in 5 minutes. Thanks, Maria.
Perfect.
And so the last thing I wanted to talk about here is, what if you have an ML problem that doesn't fit into the usual boxes for machine learning? Things like machine translation, image segmentation, game playing, some sorts of matching problems. There are lots of problems that machine learning solves, but they don't fit into any of the buckets that I've talked about so far. So just to kind of give you an idea of what's out there in the academic literature, you know, things that developers are playing with right now, but things that really aren't part of any deployed service. I just wanted to talk about a few of those things. So label sequence learning is one of them. This is, you know, kind of a supervised learning problem, except you have this additional component where your prediction depends on the last thing that you predicted, right? So when you're doing stuff with natural language, like you want to know the parts of speech of each word in a sentence, it helps you to know the, you know, what came before, basically. So outside, the word outside could also be a noun or a preposition in English, but it's an adverb in this case because it comes after this verb. And so, you know, the correct value of the prediction here is context dependent. That's a little different from treating each prediction in isolation. And there are specific algorithms in machine learning that help you solve that problem. Metric learning is another one. In this case, we want to embed all of the points in a space where things that are related are close together and things that are unrelated are far apart. So this obviously is going to have some applications, like let's say you are in HR, you've got a bunch of resumes and you want to match those to a particular position that's open. You want to send the resumes to the right people for review for that particular job opening. You can do this automatically, but it's not really supervised learning, right? You don't have a label. What you have is, oh, these two things match, these two things match, these two things don't match. So you have supervised data of that sort, and that's a little bit different from your traditional supervised learning problem. And again, there are specific algorithms we use in ML to solve these problems. And then finally, reinforcement learning. This is the sort of learning that you probably hear a lot about in the news. This is like a really complicated version of the sequential prediction case. In this case, when you, the kind of main difference between reinforcement learning and traditional supervised learning, if you want, is that when you make a prediction, which in this case is to take an action in a certain state, that tells you what state happens next. So you think of chess, where I say, okay, in this move, in this particular board position, I'm going to move queen to d4 or something like that. Now that tells you what the next prediction you're going to make is, right? Or it at least informs the next prediction you have to make, because then your opponent makes a move and then your queen is still there where you moved it before. So you have to think about, okay, if I take this action, how does that impact the next action and the next action and the next action? So this is kind of like the sequential prediction problem kind of on steroids. Like you're needing not only to predict whether or not this is correct to do in this situation, but how is it going to impact all future predictions? And so this is a much fancier sort of prediction problem that you need, again, much fancier algorithms to solve. But if you have one of these problems, don't just give up hope immediately. A lot of times you can put together a solution using parts of supervised learning and unsupervised learning kind of cobbled together in a way that solves the problem you're looking for. So even if your problem doesn't exactly fit into one of these buckets, a lot of times it'll fit into a framework where you can use the traditional tabular learning to solve the problem, at least to some degree. So a good example of this is sliding window classifiers. You can look those up online. I don't really have time to talk about them now, but this is a way to apply just the usual sort of classifier to the label sequence learning problem that I showed above. And so you can do that with languages like WisML and BigML that let you piece together bits of machine learning to form broader solutions. So quick summary, last slide here. The quickest way to machine learning is to get your data into some tabular form, and you might have to do some tricks or cleaning to do that. If you know what you want to predict, if one of the columns is the one you want to predict, then that's supervised learning. If you don't have a particular column you want to predict, that's unsupervised learning. And machine learning will usually only work effectively if you can leverage the advantages of having data instead of human expertise and an algorithm instead of a programmer. In cases where you don't have those advantages, machine learning might not be the right solution.